Hi everyone, we are talking about accumulation, and we're going to use what we've learned about volume so far to actually solve some application problems. Alright, so first one, we have a city, right, and we're given a population density function, which is given right here. The town extends for 4 miles on each side of the town square. It wants us to find the actual population. Alright, so there's a couple key things to keep in mind here. So first of all, if I think about this as like a coordinate plane, right, here's my town square in the middle. I'm going 4 in this direction to positive 4. I'm going 4 in this direction to negative 4. Okay, that's kind of what we're dealing with here. Now, if I think about my given function p as a graph, right, so it's a linear function going down. Right, if I think about this, each of these areas, these cross sections here, these areas, they represent something as they go along. Right? And if we think about what they represent, well, my population density represents, for instance, people per mile. Right? And my x-axis here, or my population represents, and my x-axis here represents my distance or my miles. And so each of these areas represents however many people I have at that specific distance. And so all I need to do is find the number of people or the area of each of these at every single point along here. Now that would be impossible to do by hand, but I can do it using an integral, right? My given bounds, my area with respect to x, I get 48,000. All right, so that's kind of an application of why we would find volume is right here. All right, let's keep going. This time I have a city and I have a circle this time. All right, my population density is given right here. And first, I want to write an expression to represent the number of people in just this shaded ring right here. Okay, well, if I think about this, if I kind of like cut this and then bend it, so I just have something straight I can look at here. All right, this right here, this represents my shaded ring. Okay, but I just stretched it, I just bent it, and I made it flat. So it looks like a rectangle. Well, this length here can be represented by 2 pi r. All right, so that's the circumference. Then my width is represented by delta r. That's what they told me. And so if I find this area, okay, so if I multiply these, my area will be 2 pi r times delta r. All right, and this represents my miles squared. Okay, this is my area. So area is in terms of miles squared. Okay, now if I think about what my density tells me, well, my density is given to me by P of R, and that represents however many people I have per mile squared. Right, so if I have people over a mile squared, and I multiply it by miles squared, those will cancel. I'm just left with people. And so all I have to do is take my area right here, multiply it by the population density I was given, that will cancel these out. And so my final answer is going to be 2 pi r times delta r times P of r. All right, so I'm just thinking about how I'm going to cancel these units. That's all I'm thinking about. All right, next they actually want me to find the population of the city, so all I have to do is integrate from 0 to 8, because that's what they told me, a radius of 8 miles. From 0 to 8, 2 pi r, and then my P of r is given as 2,000 e to the negative 0.15 r, and then delta r is the same thing as dr. All right, plug that in your calculator, you get 188,424 people. All right, and last one, we have water coming out of a tank. I started with 300 liters. How much water is there 20 minutes later? Well, again, if I just think about this in terms of what my graph looks like, right, any given cross-section here is going to tell me how much water is being pumped out at that exact moment in time. All right, so this is time and this is my rate. Okay, any given cross-section here tells me exactly how much water is being pumped out. Okay, that's area. That's what we talked about with Riemann sums. And so all I got to do is start with my initial. So I started with 300. I need to subtract my integral from 0 to 20, because that will tell me how much water pumped out between 0 and 20 minutes of my rate with respect to time. And we end up getting 250.309 liters of water. Right, that's it for this short application part. See y'all later.